Sorry for your presentation about the necessity to switch to a new nuclear energy. It's been new from the uranium to thorium. Then, to continue to introduce the debate, I will present another paper. It's about an analysis I made with a friend. It's about two extreme scenarios on nuclear energy. I think you can see the first slide. The main idea of this study was to look at what can happen if with two extreme scenarios. The first one is what can happen if we ban nuclear energy, and it was in our study it was a ban of nuclear energy in 2012, and the study has been made in 2006. And the second scenario is what can happen if we build nuclear reactors anywhere, depending on some requirements. And if I can hide, Mr. Desseux is more anti-nuclear, and I was the pro-nuclear guy. The first scenario, it's we gave the name Sunset. It was, as I said, no new nuclear reactors after 2012. The second one, we gave the name Sunburn. We development of nuclear energy anywhere, in any country, as long as some criteria are fulfilled. It's mean the first criteria is nuclear energy is optimal if we don't exceed 50% of the power demand. It's mean above 50%. In fact, some nuclear reactors should follow the demand. And I think Mr. Bata can speak after about the problem how to respect criteria of a baseload generation with a variable demand in the time. The second assumption is in average nuclear reactor capacity of 1 gigawatt. In fact, when we look at the past, operational average capacity is around 850 megawatt, and for nuclear reactors under construction, it's exactly 1 gigawatt. And the last parameter, it was at least 4 units per country. It means if you are below 4 units, the cost of all extra tasks you need to start a nuclear to operate a nuclear reactor, it's probably too expensive. But I think Mr. Cameron can speak after about this issue, and including Mr. Bishkov. And the last common assumption for the both scenario, it was we look at the different existing plants for all the countries. It means the characteristic of the energy, the power mix for the different countries, and we assume some common things like same lifespan for all coal plants in the world, same lifespan for all CCGT plants. And for nuclear reactors, for existing nuclear reactors, average lifespan between 35 to 50 years, and for new one, 50 years. For renewable sources, it's because most of them are intermittent. It means we can predict when they are going to run. We assume some fixed percentage for the baseload demand. Like for wind, it's around, we assume 5% of the average wind capacity can fulfill the requirement for baseload demand. And we can switch to the first result. It was when you look at forecast until 2030, you can see on the table the different country that should start nuclear energy. It's mean a country with power demand above 55 terawatt-hour per year, and also country with existing plants enough hold to start new nuclear reactors. It means for country like US or France, due to an over capacity, for example, for France in nuclear reactor, or in US, a big number of CCGT have been commissioned before 2005. It means the need for new baseload power plants has been delayed. It's been we arrived. This is until 2005. It was a historical commissioning period. It's mean fact, the curve is quite zero for a lot of years. And then the first dash 4 nukes, you can say, in the 70s, and then in the 80s. Maximal commissioning in 1 year has been in 85, around 37 gigawatt. And then, if we look at until now, it's more or less 1 to 3 gigawatt per year. And with our sunburn scenario, it's mean if we assume nuclear reactors anywhere, with respect of the different criteria, it's mean theoretically we should arrive to 100 gigawatt commissioned in 2030. It's mean only to understand all the industrial challenge behind this. It's mean 1/3 of the current nuclear capacity commissioned in only 1 year. This slide is about which country theoretically should increase the most the nuclear energy. Then first one, you have all the new nuclear countries, like in Europe, Italy or Spain, Poland, Finland, Czech Republic. And then if you look at, for example, France, you have only a small increase. It's due to the current overcapacity for baseload plants. And the biggest increase is mainly in countries like China, Russia, or India. The comparison between sunburn and sunset, you can see the first slide is about evolution of the nuclear capacity on a world scale. You can see no difference between the two scenarios until 2014-15, and then the decrease of nuclear capacity until 2034, the sunset scenario, and the big increase until 1,200 gigawatt. If in the 70s it was the forecast for 2000 for the nuclear capacity for the different scenario made by the International Atomic Energy Agency was around 1,000 gig. It means we arrived quite exactly the same result, but with a 30 years delay. And it's coherent with evolution of the nuclear capacity. You have second picture. It's about the nuclear production per year. It means quite no difference, around 2,200 terawatt-hour per year. It means roughly 10% of the total demand. And going down in the sunset scenario to less than 1,000 terawatt-hour and going up to 9,000 terawatt-hour. For CO2 emission, perhaps it's one of the most interesting results. It was with the sunset scenario, we can see the blue line. CO2 emission from the power sector continue to increase. And we can see it's very difficult to see any inflection in the growth. It's mean when you compare with the current situation, it's around an increase by 100%. With the sunburn scenario, it means we arrive to the result of stabilization of CO2 emission only from the power sector. In terms of uranium consumption, and we arrive to the issue that Mr. Professor Rubin said, it's about if we build a lot of nuclear capacity, its main uranium, the reserve of uranium are not enough to cover the needs. Because if you build a nuclear reactor with a commissioning in 2013, it is going to theoretically to operate until 2080. And it's why, theoretically, if a lot of countries decide to build nuclear reactors, probably it will be quite urgent to shift to another nuclear technology than the existing one. It's mainly pressurized water reactor or boiling water reactor, but it's reactors using uranium. When we update this, it's 5 years after, we have in fact two main evolution. We have two very, very different evolution depending if you look at only for the Western countries or on a world scale. For Western country, definitively you have the first change. It's more or less a decrease of power consumption. You can see on the graph is the evolution of UK power consumption, and you have the different forecasts made in 2005, 2007, 2009. And it's mean in only 6 years, the decrease of the power demand in UK, it's roughly around 50 terawatt-hours, 50 to 60 terawatt-hours. It's mean the demand is going down for a lot of countries. It's mean as long as the demand is going down, it's mean you delay any new construction for the baseload demand. The second thing is, as has been mentioned before, it's the big increase of renewable capacity, mainly wind and solar. It's mean wind and solar is around 85 gig has been built only for Europe in 6 years. Nuclear, it's a decrease by 8.6 gigawatt. And at the same time, European Union built 40 gigawatt of CCGT. And for Western country, when you look at, we have only 7 gig under construction. It means you are in situation, or for Western country, it's more the sunset scenario. Second thing, when you look at now the difference, the cost and the construction time, it seems that in our model we were too optimistic about the cost. Sorry, it's all money, it's French franc, but most of the nuclear investment for France has been made before the euro. And it's meant for the new nuclear reactor in France, the average cost is really higher than forecasted 6 years ago. Same thing for the average construction time. On a worldwide scale, you can see the demand for the power demand is mainly concentrated not in Western country, but in some country like China, India, South Korea, or Russia. You can see the biggest increase between 2006 and 2010. And when you look at the biggest decrease, it's mainly in Europe. For some country, it's due to, for example, for Norway, it was mainly due to a hydro situation. But other countries like United Kingdom, like Japan, you have a real decrease of the power demand. On a world scale, when you look at nuclear, quite no change. Only 6 gigawatt, a small decrease of 6 gigawatt. And the biggest increase, it's China. 5 gigawatt has been commissioned in 5 years. Conclusion, it's for Western country, as I said before, it's the current evolution is rather similar to the sunset. And if we continue with the current trend, it's mean by 2030 for European Union, we can have a nuclear capacity between 23 to 90 gigawatt, depending on the absorption made on the lifespan. And around 60% of this will be only in France. On a worldwide for the world, it's never a sunburn nor sunset. Very difficult to know. We have also a big spread for investment costs. It's mean the construction of a nuclear reactor in China is really cheaper than in, for example, in France or in Finland. Uranium production increased by around 12,000 tons, but the increase is quite equivalent to the current uranium available from the program megaton to megawatt. But it's mean after 2014, the conversion of the former military uranium will be finished. For R&D, it's very, very difficult to arrive to a conclusion, only because for some countries, now most of the R&D expenses are more dedicated to the decommissioning, the dismantling of all nuclear research facilities, or for the West. Remaining issue, it's always the disposal of long-life radioactive waste and all over like proliferation risk, and therefore the problem of public acceptance. When we, at the conclusion of the paper, My co-author said the glass is half empty, and I say the glass is half full. And for the time being, it's still the same conclusion, but the main issue is can we decide to use half-empty glasses rather than a half-full glass? And now I think it's I finished my small introduction for the over presentation.